Okay, so where we last left off, we were talking about DFAs, and that DFAs, as you recall, were essentially a flowchart that you would navigate via two transitions, transitions that would consume a letter and move you to a new state. And that you would always start in start state, which in this diagram I denoted with an S, but is typically denoted as an arrow pointing to it. And that it then ends up in an accept state, and if the string, when it finishes parsing the letters, if it's in the accept state, then it means the string has been accepted. If it's not in that state, then it means it's been rejected. Everyone cool remembering that? So DFAs are something that are very useful because they are deterministic. There's a finite number of states. That becomes extremely important later on. Deterministic is nice because it means that on any input, I know exactly the next state I need to go. And as a result, I can physically build this machine. I can write a simple program that will navigate you through a DFA. That sound reasonable? Everyone can see basically how you would program it up. I mean, it might take a whole bunch of switch statements, and it would. But you can program one of these up very easily with a whole bunch of switch statements. You wouldn't. Why would you need switch statements as opposed to if statements?
Just to make you less insane.
Yes, but why is switch statement? What would my switch statement for every state look like? I'll give you the first tip. Switch. What would I want to switch on?
Whatever the say A or B or 1 or 0. And
Yep.
what the input
Letter.
is.
And then what will my cases be? That's right, I have a case for every letter of the alphabet. And so that's the reason why a switch statement is already up here for posterity. Case A. Case B. And so on. I could do it with if statements, obviously, because I can always make an if statement instead of a switch statement. But case statements end up working so much better here because essentially we have an enumeration. And that enumeration is the letters in our alphabet, which, recall, is denoted by the letter sigma, not epsilon, and not curly brace, and not the number 3, or the letter E. Context clues. Gotta pay attention in this class. So, mathematicians, obviously, they see the DFA and they bother, man, why are you also hung up on reality, things that can be built by human hands? Why don't we extract that and think about, well, what if we didn't have to be so concerned about only going to one state or another? And why do I always have to consume a letter? It can't just be there, man? Hippies come up a lot in my talks. I was raised by hippies. So the way that non-deterministic DFA, non-deterministic finite automatas work is they have two major changes to them. The first one is they have the epsilon transition. The epsilon transition is special because it allows you to move from one state to another without consuming a letter. So let's draw. So what I can do is, let's say we want to accept either the string A, B, or A, A. I can write this up using non-deterministic finite automata like so, where on the start state I have an epsilon transition to two different states. And then I have an A, and then I have a B. start here. Without consuming a letter, I can go to either that state or that state. From that point, it happens to be deterministic. It need not be. You can have more than one of these in an NFA. I'm just not including a whole bunch of crazy nonsense here because I don't want to. But the epsilon transitions allow you to move for free to one of those. Here's an important thing to keep in mind. NFAs cannot be built directly as specified. Because what is happening here is it is simultaneously going down both of those paths. If one of them happens to succeed, good. If one of them fails, as long as one of them succeeds, we are still good here.
Isn't this kind of just like a logical disjunction, whereas AB or AA has to be true for it to succeed?
I mean, it is, and so, but the way we are talking about these in a mechanical sense of how do we actually process through these. And so it's related to logical concepts, but the difference between logic and finite automata is that with logic, the rules just exist. There's a set of rules that are there, and there's no process for following them. With finite automata, there is a sequence of steps that you need to follow to get to them. And there's a connection between the two because you can put these in set theoretic terms. But that ultimately the DFA, not the NFA, can be physically built. And so I can actually have someone walk through these steps and come to a logical conclusion. So this is a bridge between the world of logic reasoning and the physical world of what we have. Because logic makes jumps like this all the fucking time. And it does not care if something can be physically realized or not. We are focused on that. So we want to look at an example, one thing which is a step beyond what we can physically build, which is an NFA. And that's where this comes in. This bridges a lot of things. And so to reiterate, what goes on here is it simultaneously tries all paths until it finds ones that exist. Now, this is not actually the complete. Chart of what's going on. With NFAs, we often omit the additional states with the assumption that if you were to say get here and then try a B, that would just fail. We don't do it for the other reason that differentiates NFAs from DFAs, which is that NFAs can have multiple things, can go to multiple states on a single input. So, an NFA could also be this. That's also a perfectly valid NFA. Because on a given input, right here, we see A, we could go to either that state or that state.
So is it good to both simultaneously?
It's both simultaneously. Again, don't worry about how to build this because you can't build an NFA. NFAs are mathematical constructs. As stated, this is impossible to physically build. The way to conceptualize this is as though you're trying all paths simultaneously. You know it becomes bad when I'm tempted to say, it's a lot like quantum computation. Does that make it simpler? In fact, there's a lot of parallels between non-deterministic finite automata and the way quantum computation works. Does anyone here have any pseudoscience knowledge of quantum computation? No one can even fake a pseudoscience one.
Pseudoscience?
Yeah.
Like, I've seen French, so I pretend that I understand.
Okay,
Pseudoscience.
I understand the word pseudoscience.
Yeah.
All right, we're on the same page. So the idea behind quantum computation, and one of the ways that it's commonly conceptualized, and no physicists watching this take this seriously, is that quantum computation essentially puts a particle in a whole bunch of different states simultaneously, and then it collapses down into one of the paths. And so when you talk about quantum computation and what's called a qubit, because we're clever like that, that's That's the name for a quantum bit. A qubit. We're so clever. Anyways, a qubit can, and what we suspect can happen, and we are still trying to figure out exactly the process by which it happens, is that we can put a quantum particle in here and basically put it in a superposition of states, as though it's both going through those steps. And then whenever it were to experience an accept state in one of those paths, it would then collapse down into that path. We'll talk a little bit at the very end of the semester, if we have time, about the relationship between quantum computation and physical computation. Because it's kind of cool, because it creates a whole different hierarchy of what we can do. But failing quantum computation, these systems cannot be built. Conceptualize them as though you're trying all the paths at the same time, and if any of the paths succeed, then the string is accepted. If all the paths fail, then it's rejected. So let's walk through this. So if I were to say the string AA, simultaneously I go down there and I go down there. Now, simultaneously, I go through there and I see an A. Yay, I succeed. Here, I fail. And I fail because there's nowhere for me to go from the state on an A. One path succeeds, the string is accepted. Now consider AC. Again, simultaneously, go to both the second states. I get to there, that fails, the string's rejected because it has no path that succeeds. Does that make sense to everyone? We can formally define an NFA. You remember last time we were able to define a DFA by talking about the alphabet, the set of states, the start state, the set of accept states, and the transition function between the transition function that Matt told you on input which state to go to. Everyone remember that? The difference between an NFA and a DFA is just that. In an NFA, in a DFA, the delta function goes from the set of states crossed by the set of inputs and maps to a new state. So this is a DFA. In an NFA, the way it's defined is delta. You want me to raise this up? So the NFA is defined, the NFA version of delta is defined as going, again, from a set of states crossed by an input, and it's actually an input union with, and I'm sorry about this, the set which contains epsilon. Has everyone got that? Sigma unioned with the set that contains epsilon. Sigma is not part of, epsilon is not part of our alphabet. It's considered an additional part of it. And that now maps to, the range that this maps to is the power set of the set of states. Who discrete math remembers what the power set is? You seem really enthusiastic and no one else raised their hand and you're like,
It's like all possible sets of like each set. Like
Yes.
all the alphabets in the set.
the power set of a set is all possible subsets of that set. Okay? So, if I were to have the set here, let's say Q0, Q1, Q2. What's the power set of that? Well, the power set of that starts off with empty set, because empty set is a subset of there. It's a really boring one, but it is a subset. Empty set, and then the set which contains one element, Q0, the set which contains one element, Q1, the set which contains Q2, the set which contains Q0, Q2, the set which contains Q0, Q1, because apparently I did them out of order for whatever reason. The set which contains Q1, Q2, and the set which contains Q0, Q1, Q2. That's the power set. Keep in mind, when I talk about this, this is saying that's the set of possible things you could map to. That's not saying every transition maps you to every one of those. That's just where it could take you. So let's come up into here, and let's take this. I'm going to draw it a little bit bigger, and let's talk about what the delta will look like for this one. So A, B, B, Q0, Q1, Q2, Q3, Q4. Again, this delta is defined for every one of those values. So we're going to make our delta table. Let's make it over here. Let me just make sure. I want to make sure I'm recording it so you can see. Yeah, you can see it over there. Okay, good. The delta table for this. A, B, epsilon. Q0, Q1, Q2, Q3, Q4. On Q0, where do I go on A?
Start.
No, where, I'm at Q0, I need to draw Q1 and Q3. So where the delta will take me is it will take me to the set which contains Q1 and Q3. Now, I haven't written out the power set through Q0 through Q4 because it's really long. Anyone know the size of a power set? It's combinatorics, except order doesn't matter. What?
5, 2, 3.
You guys can figure that out later. I'll leave it to the reader, to the exercise to the reader. Anyways, really big. So you guys can figure it out. We'll talk about it next class. So Q1, Q3. Where do I go on B? Yep, I go to empty set. I don't go anywhere. Where do I go on epsilon? Empty set. Q1, where do I go on A? No, Q1 is up here.
Oh.
On A. Oh, wait.
Okay, there you go.
I need to go to A. I go to the set which contains Q2. Where do I go on B? Empty set. Empty set. Q2. Empty set. Empty set. Empty set. Q3. Empty set. Q4. Empty set. Q4. Empty set. Empty set. Empty set. Is everyone good with this?
just one question, when you have the forking, or the forking states, does the letter you use actually get to one of those two states, count in the input, like AA instead of AA and AB instead of just A and B?
What do you mean?
With that automata,
Uh-huh.
I mean, do you only not count the character when it's epsilon?
Right.
Okay.
If you go to a path, so if I were to say replace this with epsilon, this would accept the string A or the string AB.
Okay. If they were both epsilon, they would accept A or B?
Right.
Okay.
Does it make sense? I really hate allergies. How many more drugs can I be on? The answer is much, much more. This is the idea of an NFA. Now we get to which is an interesting thing, which is that I've drawn this up here. Do you think I could write this as a DFA? How would I write this as a DFA?
You have Q0.
Yeah, let's start erasing some stuff up here. I realize before we get into this process. You guys mind if I erase everything aside from this? Alright. I'm gonna leave the transition now. Okay, so
You
right.
start with Q0, then you go to Q1 through A, and then Q2 through A and B.
Wait, what? So like this, and now what?
And then you can go through to Q2 with A and B.
Like that?
Yeah.
Yep. That is a DFA version of an NFA. Yeah. Really should bring clinics to class. What are you gonna do? So here's a theory. Do you think I could take any NFA and come up with a way to turn it into a DFA? No matter how crazy that NFA is, I can turn it into a DFA. I need some commitments here. Let's take a vote.
Well, she's like that since she's in a theory of computations.
Don't trust me.
She could be lying. I've told her to lie throughout the class to throw you guys off the track. Okay, so yeah, so let's take a vote. How many people think yes? How many people think no? I appreciate your bravery and your incorrectness. Yes, you can. Not only can you, but the trick is right before your eyes. Woo. Here's the thing. So I really don't want to write out. The power set of this. It's really big. What you do is you come up with the original, essentially the formula for it is come up with the delta transition. Now what you do from this point is rather than saying, hey, Q0 can take you to Q1 or Q3, don't worry about that. Instead, make it so that it actually goes to the set Q1, Q3. And keep on adding more sets. So Q1 and Q3 can now take you, Q1 on A can take you to Q2, and Q3 on B can take you to Q4. So let's start off with the way you do this. the first thing you do is you have your Q0, and we're doing this without epsilons first because I like you guys. You start off with your Q1, and in the absence of epsilons, your Q1, your Q0 is just your Q0. You then say, on an input A, where can it go? Well, it can go to the set Q1, Q3. And so the label of this state is no longer Q sub something, it's actually the set which contains Q1 and Q3. And I actually lied to you a little bit earlier. It's not Q0, it's the set containing Q0 is the label there. Now, Q1 on A, where can it go?
Q2.
It can go to Q2. So it goes, where can Q3 go on A?
No.
Nowhere. Right. So we combine all the places you could have gone on Q1 with all the places you could have gone on Q3, and that gives you the new set of where you can go on the input. So this takes you to the set of Q2. If in there is an accept state, then the whole thing is an accept state. Any other question you're playing with your hair? Great, that one actually erases.
Aw.
Why are all the markers in the back?
Those math guys, they just work it up.
Yeah, Jay Lee just goes around all the boards until they're all filled up.
He does. I walked in here once on a Saturday and just everything was filled.
It's really funny. Yeah, I think Math Lab also likes working on those back ones too, which is why the desks are all wonky every time. It's nice. Because Q2 is an accept state up here, and Q2 is in this set, that means that state is an accept state. Now, on B, where does Q1 go? Empty set. Not really interesting. Where does Q3 go on B? Q4. That's the accept state. This is a DFA version of the NFA. Now, Riley correctly realized, hey, I can make this smaller. We are not there yet. We will talk later about how to minimize a DFA. But you'll notice, oh wait, there's an interview question label up there. This is a very, very, very common interview question. It's actually part of a multi-phase interview question. We're not done with the whole thing yet. The whole interview question will be, take a regular expression, turn it into an NFA, turn that NFA into a DFA, turn that DFA into a minimal DFA. That will be the full gamut of the interview question and will 100% be on the test.
You say that in theory, but that question never come up.
I know it never came on your, it never came on your exam, but this is a, what? We don't actually talk about minimizing in theory of computation because from a math point of view, it's useless. From a real world point of view, it's really important. From a math point of view, it's like, what do I care? Done. It's a DFA. I can physically build it. So what if it has 5 kajillion states? That's a future programmer's problem. That's fine. In this class, however, you guys are trying to get jobs. So you'll actually need to minimize it. And we'll talk about the process of minimizing later. We'll also talk about what a regular expression is and how you turn it into an NFA later as well. So let's do another example of this. So I've done this now without epsilon transitions. Let's draw another NFA with epsilon transitions. I'm gonna erase all this nonsense, you guys. Cool with that? Okay. So Q0, epsilon A, Q1, Q2, B, A, going crazy with these A's, Q3, B, Q4, B, A, A, A. You know, except say, turn this into a middle of the FAQ. Well, okay. Well, actually, sorry, I'm gonna change one of these. There. You bastard. Now I've got to solve it up here in front of you with a recording judging my every move.
You've done this seriously.
What?
You've done this seriously.
I have.
If you do anything wrong, the internet will start screaming.
Oh god. Honestly, if I do something right, the internet will start screaming. So clearly, this professor is worse than Hitler. Why? He worked it up correctly. Again, why? It's like explaining to my 3-year-old why things are when he keeps asking why. You say it enough times, you're just like, because I love you. And like, oh, end of questions. If you're telling someone they're worse than Hitler because you love them, you have a dysfunctional relationship and need help. Okay. So here is our NFA, and I don't know why I'm labeling it. But let's actually go through and do a DFA. Would anyone like to try this? Okay. Okay, so let's talk about what happens here in the very beginning. I put an epsilon in the very beginning because with epsilon transitions, they act as, I guess they're the head crabs of the One Place Half-Life.
Oh,
yeah. I don't get those references from video games. I only read Charles Dickens. So it automatically absorbs the state next to it. And this is true even for the start state. So our start state is no longer the sole set which contains Q0. It's actually now the set which contains Q0 and Q1. And that is our start state. If there was another epsilon transition here, then it would include that as well. You keep on following all of the epsilon transitions and glom them into one state. Everyone cool with that? I can make it without actually adding any additional work by adding a whole bunch of epsilons up here that then lead to a dead state. And then put all of those states in there as well, which would add no additional work to me. But any chain of epsilons you get, as long as you can reach there from an epsilon transition from the beginning, or whatever state you end up in, it's automatically absorbed into that state.
So A3 and A4 would be treated as one state or one state?
Not always. When you arrive there via Q3, you are just in Q3. When you arrive to Q4, then you include Q3.
Okay.
That's gonna get. What's in the start state for it? Not the one with the set. I can't read.
This one?
Yeah.
Alright, I'm just going to write these without the curly braces. Just know that they're there. 0, 1. Does that sound good? Just know that there's curly braces there in your mind. Okay, now on A, I have to figure out, I don't have to draw that whole chart for each of these. I can figure it out by processing through these. It can be a little bit more challenging this way, but I find it a little more rewarding because I have to do a lot less work. So where do I go on A from Q0?
Q2.
Can I go anywhere to A on Q1? No. So on A, I go to the set containing Q2. Q0, Q1, where can I go on B? Where can I go on Q0? Nowhere. Q1, I go to Q3. Now, AJ, notice that it's not Q4 because you can't epsilon transition your way into there.
Right, see, so if it's one way, then it only applies one way.
Okay, now Q2 on A, where can I go?
It's that other one D, that
Oh, yeah.
transition.
Q2, where can I go on A? Q2, Q5, and that's an accept state because Q5 is an accept state. Okay, Q2, where can I go on B? Yep. I tend to draw them in this as order way as I can because it makes it a lot easier for me. I tend to draw A's in one direction, B's in another. I will never give you, you will never see a C in any of my examples in this class because
It doesn't come out of it.
yeah, it's just difficult to draw. We've got enough going on here. Okay, so it goes to Q4. Where else is it? What else does it do?
So epsilon.
Yep, there's an epsilon there, so we also get a Q3 for freeze. So you see that because we get into Q4, there's an epsilon transition there, so you automatically get the Q3 as well.
The top one's Q4, that top one's Q4, Q5?
Q4, Q3.
Okay, but what's the other one that?
This one?
Yeah.
2-5.
Oh, okay.
Q2, Q5. Do you want me to just write the numbers and not bother subscripting?
Yeah, that might be.
So how's Q2 and Q5 when there's no epsilon transition?
Nope.
between them?
From Q2 on A, you can go to Q2 and you can go to Q5.
Oh, okay.
There's two ways you can states can join up.
I see, okay.
Everyone cool with that? Okay, Q2, Q5. Where can you go on B?
Q4.
You can go to Q4 and Q3, right?
Epsilon.
So, hey, we already have that. Does that make sense? We already created a state for Q4, Q3. So why bother drawing a new one? Just go back to that one.
So if Q5 went to like on B, if it went to like a Q6,
You'd have to draw a new state. Wait, what?
well,
So you're saying if I had another state here,
Yeah.
like Q6,
Yeah.
then I couldn't have that sheet. I would then have to go to a new state, 4, 3, 6. But it doesn't. Does that make sense? It just happens, yeah, Q5 goes nowhere, so. Q2, Q5, where does it go on A?
Q2.
And Q5.
Self-loop.
It's self-loop. See, it can go either there or it can go there. Beep.
isn't it? Oh, okay, never mind.
Yeah.
I see the arrow.
Okay, 4, 3. Does it seem like I'm doing some type of depth first search through these? Oh my god. You don't have to do it depth first search wise. It makes your life a lot easier if you do. Because that way you make sure you don't forget one of them. But yes, you want to go through it in a depth first search. Or breadth first search, but be consistent about it. Depth is easier to do by hand. It's amazing how that works out like that. Alright, okay, so 4-3. Where do I go on A?
Q2.
Q2, Q5.
So on Q4, Q3, I can go to Q2, or I can go to Q5. Q4 are really not doing anything for us. So yes, it's Q2, Q5. Is that what you guys said? And,
What?
so on A, Q3 can go to Q2, Q5, Q4 can't go anywhere on A, or B, just epsilon. So, goes back to there on A.
Glad I made this bigger than you did.
Okay. Q3, Q4, where's it go on B? Yeah, it's a self loop. Q3. Where do you go in A, where do you go in B? A first, where do you go?
Q2, Q5.
Where do you go in B?
Q3, Q4.
Nope, it's not a self loop. There you go. Does that make sense now? Again, it happened here by coincidence because I'm setting up an example that wouldn't take us a year to solve. That we only had one accept state here and one accept state here. Usually it's the case when you're drawing these out that you actually end up having multiple accept states, whereas you may have had only one in the original. Because it's wherever Q5 would occur is now an accept state. As another example, and the regular expression from the upper left, and we'll get to that in a bit, is here we have an NFA, we've got epsilons coming on the inside, A is going to C, B is going to D, D is going to F, F is going to G, for the epsilon. The transition, the DFA version of it is like so. I don't want to step through this because we're running out of time, but it's another example for you guys to have in the slides of what's going on. The reason why I wanted to point this out is that notice that we do have two accept states here, and the reason why they're both accept state is because they both have
That one compresses quite nicely.
What? Yeah, it actually gets even smaller. And then to help you guys further, I also have step throughs as well. So we don't need to step through that, but that'll be helpful for your reference later on. We don't have time to talk about regular languages today, but we have a minute 30. We really don't have time to do it. I'm going to repeat this next class anyway. So, you guys want to tell Deshaun that. So, any questions about this?